So do you still see well? Okay. Yeah, I'm very glad to be here. So thanks for inviting me. I was a bit afraid that I would not have a screen big enough to see all the calculations I'm up to, but I trust it now, though. So those in the back might have some difficulties at some time, but I think we are okay. My aim in this talk is quite modest. I just want to explain a method of how to make sense of an integral of one rough function with respect to another rough function, to put it into the words of Terry Lyons. So at least in the beginning of your theory, you were looking at this problem. Or I could also put it into the words of the regularity theory, in which we would be interested in multiplying one distribution with another distribution, and one of those distributions might be with negative regularity. So the problem I was looking at would be this, but if you take it as looking at the problem of defining the integral of one rough function with respect to the other one, you basically face the same problem, because you can view it as integrating f with g dot with respect to time. So you might view it this way or this way. Our method, in any case, is related to a translation of this problem for continuous time functions into a sequence space, which is created by developing the functions we face, f and g, by Harshauder expansions. So instead of looking at those functions as functions of a continuous variable, you could look at the development coefficients with respect to Harshauder expansions, and then it's a problem of sequence space. And this is exactly what I'm going to. So, well, if you want to have an example of why this is related to regularity theory, look at SPDE, some singular SPDE, then you have to multiply two singular distributions here, and this is exactly what we are facing, and what was also the goal of our approach. Okay, so here we are. So I take my function f and my function g, and I expand it into Harshauder expansions. I come to the sense of HPM and GPM on the next slide. So you have the Harshauder expansion of your function f. You do the same expansion for your function g, and then you have a double series, and you have to integrate one Schauder function with respect to the other Schauder function corresponding to g. And here are the development coefficients that do not play a role in the process of integration. But this makes sense, at least for term by term, because each of those Schauder functions is Lipschitz continuous, and so you can integrate one with respect to the other. Of course, this is a problem of summation. So this is what we have to face. So this is just in a nutshell what we are going to do. So you have a continuous problem of functions of continuous variables, and you translate it into a sequence space language. Okay. Here are the half functions, and I was a bit afraid that you would not be able to see these pictures here. So HPM of t is this function. So you fix dyadic generation number p. Let's say p equal 1, for which I have two intervals. The interval from 0 to 1/2, and the interval from 1/2 to 1. And so I have two intervals. For the first interval, so for m equal 1, I take the first interval, I divide it into 2, and I take the function to be a constant positive on the first half and a constant negative on the second half. And then I continue with the second interval in the same way. Okay, here I have, in the second generation, I have 4 intervals. In the third generation, I have 8. Okay, now I come to the Schauder functions. The Schauder functions are just the primitives of the Haar functions. So in the first case, I integrate the Haar function with respect to the Weg measure, and that will give me these sawtooth objects. So on the first half of the unit interval, on the second half of the unit interval, I get the second one in the first generation, and in the second generation, I get 4 of them, like this. And so the numbering with respect to m goes from the left to the right. Yeah. So if, for example, in generation 2, the first quarter of the interval, the second quarter of the interval, third, and the fourth quarter. Okay.
You wouldn't have a 0.
Yes, that's just the constant one. And a linear function for the Schauder. Yeah. Okay. Okay. So how does that work? So how do I get the Schauder series of a function that I was exposing on the third slide? First of all, we look at functions that have square integrable derivatives, like f here. So if it has a square integrable derivative called f dot, then what I do is I take a Haar extension. The Haar functions are a complete orthonormal system of L201. I'm on the unit interval. So I take a Haar extension of f dot, and I have to integrate it in order to get f. Now I interchange summation and integration, and that gives me, so the Haar coefficient is here, and that gives me integral from 0 to t h p and s ds, which is the Schauder function. So this is how I get a Haar Schauder expansion of a function. This function now having square integrable derivative, but you'll see in a minute that this is not essential because my Haar functions were constants. So if I take the Haar coefficient of f dot, then what do I get? So I take my endpoints of the nth interval. So I'm in generation number p, and I fix interval number n, which goes from n minus 1 over 2 to the p to m over 2 to the p. Here is the midpoint. And at the midpoint, the Haar function changes sign and becomes negative. So if I take the integral of the Haar function and f dot, then what do I get? I get the increment of f over the first half of the interval, t1 pm minus f of t0 pm, minus the increment over the second interval, which is f of t2 pm minus f of t1 pm. So I get this double difference, okay, times the square root of 2 to the p. Okay, now I have to explain how those coefficients are bounded, because I want to translate everything into a sequence-based language. So imagine you take this quantity here. So you have an integrand and an increment over the first half of the interval minus the increment over the second half of the interval. You divide by the alpha power of the interval length, and you estimate by the Hölder norm of f, which is the supremum over all differences of f divided by the length of the interval power alpha. But then I can compensate by length of the interval power alpha in the numerator, and this gives me the 2 to the p times minus alpha. Yeah, and the 2 to the p over 2 comes from here. So this is in fact an estimate for each of the coefficients in my development. Okay? Clear so far?
Can I ask you a question?
Yeah.
So here p doesn't depend on f.
No. P is just the number of the dyadic generation. And I let the dyadic generation run through all positive integers. Yeah. Okay. So now I have to ask to answer the question, in which space does this Harshauder expansion converge? So here we have the Harshauder expansion for a function which is has still a square integral derivative. But I claim I can in fact do this development in the space of alpha Hölder continuous functions. Now that poses the question, how well is the convergence of this series? So I have to take the series rest, so all terms up with an index bigger, with an index dyadic generation bigger than k, let's say. And then I have to estimate the contribution of generation number k, number p. So let's fix the generation p. So in the generation, I have the intervals from n equal 1 to n equal 2 to the p, okay? So for each of those coefficients, I have an estimate, which was given on the previous slide here. And for the Schauder functions, how can I estimate it? So first of all, you see that the intervals are pairwise disjoint within one dyadic generation. So since the support of the Schauder functions are just the intervals on which they are defined, the support of the Schauder functions within one dyadic generation are disjoint. So if I take the sum of the Schauder functions, the infinity norm over the sum of the Schauder functions will be the same as the infinity norm of one of the Schauder functions. And what is this infinity norm? Here is my here is another drawing, so I hope you can see. So here is my Haar function in for a function of generation number p with number n. Okay, so on the first half it's positive, on the second half it's negative. Now, if I take the primitive of it, the integral function, then I increase on this interval and I decrease on the second interval, and in the end I'm back to zero. Yeah, so I'm 0 here, and in the meantime I'm increasing with a slope 2 to the p over 2, because that was the size of my Haar function. So 2 to the p over 2 for the length of 2 to the minus p minus 1, which gives you 2 to the minus p over 2 minus 1 as infinity norm of the Schauder function, and therefore I can estimate here. So I have a general estimate on the coefficients if my function is alpha Hölder continuous. So the alpha Hölder norm is finite. So in this case, I have this estimate, but I can compensate the 2 to the p over 2 by multiplying with the Schauder function even better. So my estimate for the contribution of the term of the p dyadic generation is just 2 to the minus alpha times p. And that is a geometric series. So if I sum it from k to infinity, I'm getting this quantity. And you see, so if the alpha Hölder norm is finite, then the whole thing has to converge with respect to alpha Hölder norm. That is, I get an expansion within C alpha, the space of alpha Hölder continuous functions. Okay, now back to the sequences. Okay, I do a change of notation. Yeah.
Why are you using infinity norm? Because it seems a bit strong. Is it?
Well, I want, for example, uniform convergence for that.
That's true.
For that, infinity norm is the right one. So if I want the limit to be continuous again, for instance, okay, then you need infinity. Okay. Okay. So now I change the scale a little bit. I blow up my Haar functions, HPN, so they were 2 to the p over 2 high or low, and I blow them up with another 2 to the p over 2. I'm not interested in orthonormality anymore now, and I blow up also the Schauder functions by the same amount. So now, if I develop one function f into a Haar-Schauder expansion, so the old system is here, and in the new system, I have a factor of 2 to the minus p here to compensate for taking 2 to the p over 2 for chi and 2 to the p over 2 for phi. So I compensate it here. But now chi pm has height 2 to the p over 2 times 2 to the p over 2 to the p. So this 2 to the minus p times chi pm is just an indicator function, or a difference of two indicator functions. That will be important in what follows. So I now describe my functions as, well, Schauder, modified Schauder times FPM, and FPM is this coefficient. Okay. And now in the modified Schauder system, so in the old Schauder system, my Schauder function had 2 to the minus p over 2 minus 1. In the new, it has just 1/2 because I blew up with 2 to the p over 2. Okay. So, and this was this development coefficient now, since I was saying that this function in green here is the difference of two indicator functions, so you just have to get the difference of the two increments. That's all. And this already tells you that my developments converge. So this development, so up to dyadic order p is just a linear interpolation of f on the dyadic points given by the intervals. Okay. So now let me introduce.
So do you have an idea of the rate of convergence in the end that you get?
Well, on alpha Hilbert space, it's just this rate of convergence. That's what I claim in this slide here. So I now define a sequence space, Hölder norm, just FPM, the development coefficient with generation P, a dyadic interval number M, multiplied by 2 to the P alpha and take the sum over P and M. Now, since this is, so 2 to the minus P over 2 times this is FPM, and 2 to the P alpha was here, I have this to take the sum of 2 to the P times alpha minus 1/2 times this coefficient. But this coefficient, remember, was just the inverse of the quantity I have now. Yeah, so this was the inverse of the quantity here. So I'm getting just equivalence of the alpha Hölder norm on the sequence space with the alpha Hölder norm on the function space. Okay.
Sorry, the result specifically depends on this point of R from the orthogonal system.
Well, I have chosen the Schauder system. So if you take trigonometric functions, the game will be a different one. Okay. So, well, this is Czechielski's theorem, which expresses this. You take, if you go from alpha Hölder space of functions of a continuous variable, C alpha, into L infinity, then this mapping will be an isomorphism between function space and sequence space, and this is basically what our analysis is based on. Back to integration. Now I take an f in C alpha, a g in C beta, and I ask myself, if I look at their expansions by their Harshauer expansions in the modified Harshauer system, f and g, then what can I learn about integration? Now, as I said on the third slide already, here I get a double series. If I take the integral of f with respect to g, I get a double series. Here are the coefficients, and here are the integrals of the modified Schauder functions with respect to the modified Schauder functions. Now, the derivatives of the Schauder functions are the Haar functions. So, in fact, I have to deal with integrals from 0 to some variable within the unit interval, phi pm, so the Schauder function, times Haar function, phi qn, yes. Now I have to take into account the dependence on time t of this quantity. And this, and to study this in terms of my sequence spaces, I have to develop another term. So I have to take those coefficients here, phi pm, phi qm, and since my integral is still a function of t, I develop once more with respect to Schauder functions. So I take 2 to the minus I. Remember, this was just the difference of two indicator functions times pi ij. And then I have, well, a somewhat awkward looking quantity that depends on 6 parameters. And I will have to deal with how large this can become in order to tell you the truth about the integration of f with respect to g. Now, how large can they become? So I take my quantities, my coefficients of the integral with respect to another Schauder system, and I claim that this quantity is small, so 2 to the minus 2 times the supremum of the development I. So this is dyadic generation number I, dyadic generation number P, dyadic generation number Q. So you take the supremum of the three here plus P plus Q. There is only one case in which this gets difficult, and this is the so-called resonant case. And the resonant case plays an important role in this whole business. So in case the Q dyadic generation is equal to the I dyadic generation, which I develop my integral, I only get a very weak estimate by 1. So this is the so-called resonant case, will play a role. To give you an idea of how to prove this, well, let us just single out one case. So I take the case where I is less than Q less than P. So the I interval is the longest, then comes the Q interval, and then comes the P interval. Okay? So in this order. So the I, since I develop with respect to 2 to the minus I pi ij, I said this function is just the difference of two indicator functions. So from T0, Tij0 to Tij1, this is the first half of the interval whose difference of indicators I have here. So here I have just the difference of the, here I just have an indicator function, and then I have the product of phi pm, which is a Schauder function. So that's the blue function here, and phi qm, the red function here, which is a Haar function. Okay, now how big does that become? Now, obviously, since my development function here is just 1 on the whole interval, I'm getting the integral of phi pm multiplied by 2 to the q. 2 to the q times the integral of that function, but the Schauder functions in the modified system were just 1/2 pi. So I'm just getting, well, the area of that of that triangle, which is of the order of magnitude 2 to the minus p. So I get 2 to the minus p times 2 to the q. But now if you take the balance, you can interpret it just in this way. P plus q minus twice the supremum of I, P, and Q. The same as I've written here. So you just reproduce this formula. And in the other cases, it's just the same. These estimations are very elementary, but a little tedious to write down. So now let's come to this lemma that I was proving before in terms of the Paley-Litwood language. So the contribution of one dyadic generation, which was sum overall m fpm phi pm before, I just write it as delta pf. That's the contribution of dyadic generation number p for my function f. So I write SQF as the sum overall dyadic generations below Q, as below P. Okay, so the Paley-Litwood packages, as we say, of all dyadic generations below P. Now, well, just remember, F in C alpha just meant that this norm is finite. Now, this norm was 2 to the p alpha times, well, I took FPM here, and then I took the supremum of P and M. I could quite as well take the supremum over delta PF, because that takes care of the dyadic of the whole sequence of dyadic intervals of generation. So this is my alpha Hölder-norming sequence-based terms. And then if I now translate my lemma on the previous slide into the language of Haley liquid packages, I have to sum over the whole overall contributions inside one dyadic generation. And so the term, the -2 here gets lost, and I just left with the -1. Everything else, it still needs a little bit of work to put this quantity down, but it's yeah. So you get the I package of the product of the P and the Q package is bounded by this quantity times the infinity norm of the packages, the product of the infinity norm of the packages. Only in the resonant case, in which you have I is equal to Q, you get just an estimate by a quantity 1. Okay. So now comes the essential thing. You develop your integral of f with respect to g into three into three quantities that behave very differently with respect to convergence. So you take the sum over all packages delta PF and the sum over D delta QG, and then you separate P less than Q, P bigger than or equal to Q. You single out those for which P and Q are equal. This is the green part, the symmetric term, and then you have one term for which I write D delta QG here, and the sum overall P less than Q, that is SQ minus 1, yeah, and the other term vice versa, yeah, with the sense interchange. So this is my symmetric term. It will turn up later on, and I take now this term here, and I do an integration by parts. So I take the integration over to the other variance from F to G. Now, what does that give me? It gives me a boundary term which is sum SQ minus 1F delta QG minus something that has a delta QG DSQ minus 1F. Okay? And now this term plus this term are taken together and give a so-called antisymmetric Levy area. So the green term is the symmetric term, and this red term here is the para product of F and G, and the difference of this blue term with this blue term is the antisymmetric Levy area, which is here. So I have decomposed my whole integral into, well, here is another writing of the symmetric term. So I have decomposed my integral into para product, symmetric term, plus Levy area. And now you see that those three objects have completely different convergence properties. Now let us just verify it in terms of the symmetric term. So for the symmetric term, I can say delta IF, delta IG, infinity norm is less than the product of the infinity norms. And then if I want to make alpha norms or beta norms out of them, I just have to multiply by 2 to the minus I alpha here, 2 to the I alpha here, take the supremum over I, and multiply by 2 to the I beta, take the supremum over I, but then I have 2 to the minus alpha plus beta I free for compensation. So this is my estimate. So this is true for all parameters alpha and beta for the symmetric term. So for the symmetric term, I get this inequality. For the para product, I get this inequality. I have the infinity norm of F and the beta norm of G. And for the Levy area, I get an estimate for the alpha plus beta norm, but only if alpha plus beta is bigger than 1. only if this is the case. So that these three different kinds of behavior of the terms I split the integral into then give rise to the theory of the Young integral. If I have alpha plus beta bigger than 1 for the Levy area to converge, f in C alpha, g in C beta, then this integral converges, this integral exists, and I get this estimate. Yeah. If I subtract the power product, I even get a better estimate. I get it in alpha plus beta. Okay. So this was the story of the Young integral. Now, what if you 1 minute? Okay. So what if I'm in the rough path, in the real rough path regime? Then I have to have another ingredient in my analysis, which is the so-called controlledness of paths. Controlledness of paths is something like the Taylor expansion of a function with respect to the first term. If I subtract the first term, I get something more regular. Now here we extend the notion of Taylor expansion into fractional powers. Yeah. So this is the notion of. So if I was writing fxx here, it was exactly the controlledness of paths in the theory by Gubinelli. Now, we changed this by just subtracting the para product of fx and x. This way we avoid problems of resonance. And if we just subtract that and require that after subtracting this rectified term, we get a C2 alpha continuous function. If we start with an alpha continuous function, then we call this path paracontrol. Okay, now, well, we define a norm on this space of control, paracontrol functions, and then you see immediately that we will succeed in getting something. If I take the Levy area now, not of, so I suppose that I have a control path X, and that this is in fact a multidimensional object, because Levy area of just one function with respect to itself does not make sense. So I have a multidimensional object. So Levy area of f minus this correcting term with x makes sense, because now I have this to be 2 alpha Hölder continuous, and this is alpha Hölder continuous, so that 2 alpha plus alpha is 3 alpha. So if 3 alpha is bigger than 1, the Young theory from the previous slide takes over and gives a result. So in fact, what else one has to do is just to make sure that this quantity, so the Levy area of the para product with x, makes sense. And this is done in a so-called commutator estimate, which is true, which has to be done. It's some work. But I cannot explain it in more detail here. So if the Levy area of the product of the para product with x, it can be estimated by the integral of the derivative with respect to the Levy area, and this is continuous in the 3 alpha Hölder norm and can be estimated by that. And so the integral is well defined, provided the Levy area exists, and here is the theorem. So you have x in C alpha, fg in D paracontrol, and then the Levy area of x with respect to itself, multidimensional now, exists, and then you can show that the integral of f with respect to g exists and can be estimated in the x alpha norm by these quantities here. Okay, so that's the story of the rough path.
So thank you for your talk. Maybe there are some questions.
Yeah.
Is it obvious that dx alpha is non-empty?
That what, the x alpha?
Dx non-empty, like this set which is defined.
Dx alpha.
Exactly.
Yeah, it is. So if you take, for example, a stochastic differential equation, there will be elements inside. if F is, well, has certain regularity also.
Are there other questions? Yeah.
About the definition of the union integral, are you able to cover other integrals using this approach?
Which one?
What your union
This integral here,
no,
the Young
before-
integral.
before the first, yes.
the Young integral.
Yes, that's
Oh.
right.
Well, it's just the same integral as you get if